Hi. So we're thrilled to have our third public speaker, public talk in this special year on combinatorics and computational complexity. And Jacob Fox received his PhD from Princeton, where his advisor was Benny Sudakov, who's here. And that means he's also the academic grandson of our first public speaker, Noga Alon, was also like a long-term visitor to this program. And we should have maybe had just, I think, like just this family, this family can fill out a lot of great talks, very relevant to this postdoc. So he was faculty at MIT until he left us here in Cambridge for warmer climates. At Stanford, he received many awards, including the Packard Fellowship and the Oberwolfach Prize. And he's one of the leading world experts in Ramsey theory, which he has studied since high school with a project that won the Carl Menger Memorial Prize in the Intel Science competition on rainbow arithmetic progressions. And this Ramsey theory and the dichotomy between structure and randomness is an area that we keep discovering more and more applications and connections between that and other areas, in particular computer science. So this is what he'll talk about now. And if you like the talk, and I'm sure you will, please also look up at the workshop we're having next week in the CMSA on extremal, what's the exact title? Extremal and probabilistic combinatorics, and there will be a lot of great talks. So let's welcome Jacob Fox.
Thank you. Can you hear me? Can you hear me?
Yes.
Okay. Thank you. It's a great pleasure to be speaking here at Harvard. There's this fantastic year program going on now in combinatorics and complexity theory at the Harvard CMSA, which is close by. And this is one of the many activities that's going on there. So there's a great workshop next week if you like this area. So I'll be talking about arithmetic patterns, games, and the quest for fast algorithms. I'll start off by talking about the prime numbers, and then I'll move on to graphs, and then I'll talk about the game of set, which are all seemingly very different topics, and I'll show how they're closely related and how we've learned about these other problems from them. So we'll see some very interesting connections. So starting off with the prime numbers, a prime number is any natural number greater than 1 which cannot be factored as the product of two smaller numbers. So these are smaller natural numbers. So these are the building blocks for the integers. And they fascinated mathematicians since the ancient Greeks. And they're also very practical. So the way that we do now encryption when we want to transmit data is using the RSA algorithm. And it assumes that factoring integers is a computationally intractable problem, that it's hard, it takes a long time. And so understanding the primes better may lead to the answer of whether or not this is computationally intractable. Many people now think that it's not, and that you could break RSA, and that would have lots of very important implications. I won't go into that, though. We'd like to understand the prime numbers. So here's the first few prime numbers, 2, 3, 5, 7, 11. And the first question one might ask is, are there infinitely many of them? And that was answered by Euclid a few thousand years ago. And then you can ask, well, how numerous are they? If I look at the first n positive integers, how many of them are prime? And this is given by the prime number theorem. This is a famous result from the 19th century. The number of primes up to n is asymptotic to n over natural log of n. So while if you take a typical random number out around n, the probability that it's prime is 1 over natural log of n. So it's typically not prime, but there's still a lot of them out there. And we'd like to understand patterns in primes, and these questions have been studied for a very long time. So I'll mention a few open problems. Each of these problems, these conjectures, go back before the country was started. The They're very old. So the one is the twin prime conjecture. There are infinitely many pairs of primes that differ by 2. So an example is 29 and 31. They're both prime, you can check. They differ by 2. And are there infinitely many such pairs of primes? And this is, there has not been much progress on this until recently. There was this breakthrough work of Zhang where he proved that there are infinitely many pairs of primes whose difference is at most 70 million. And there was further work by Maynard and Tao, and they brought that 70 million down to 200 and something. And there's very good reasons why we haven't brought it down to 2. So that's still a very hard problem. Another example is the Goldbach Conjecture. It says that every even number at least 4 is the sum of 2 primes. There was a book when it came out about 10, 15 years ago, Uncle Petros and the Goldbach Conjecture, and it's a fictional book about someone who thinks they solved the Goldbach Conjecture, and the publisher offered a big prize, I think it was on the order of $1 million, if someone solves the Goldbach Conjecture within some amount of time. And of course they didn't solve it, but this is a hard problem. And there still has been some progress on this. In the 1930s, Vinogradov proved that every odd number that's sufficiently large is the sum of 3 primes. And more recently, Helfgott showed that every odd number at least 7 is the sum of 3 primes. So that closed the gap for 3, but bringing it down to 2 also has very good reasons why it's challenging. That adding 3 numbers is a lot smoother than adding 2 numbers, or 2 sets of numbers. And a third problem is primes in arithmetic progression. There are arbitrarily long arithmetic progressions in primes. So an example of an arithmetic progression in primes would be 5, 11, 17, 23. That's a 4-term arithmetic progression. I mentioned 4 primes, and they're evenly spaced out. They have a common difference of 6. And the question is, can you get arbitrarily long arithmetic progressions where each number is a prime? This has now been solved by Ben Green and Terry Tao about a decade ago. And there's some very interesting mathematics that go into it, and I'll tell you about the mathematics shortly that goes into it. But the general idea of how we try to understand the primes now is through a heuristic that the primes behave like a random set. So instead of actually looking at the primes, it's a deterministic prime. 5 is prime. It's not a half chance that it's prime. It's definitely prime. But instead of actually looking at the primes, we'll make a different set. We'll pick a random set, and we'll look at properties of that set. And then we'll look at the primes and say, well, if that set should have this property, then the prime should likely also have this property. So what do? It's called Kramer's model. It was introduced a long time ago. We pick a random set of integers. And the probability that we pick the number n to be in our set is going to be about 1 over natural log of n. So for each integer n, we're going to pick such a set, and we're going to do this independently for each n. And so you get a random set. And this actually behaves in many ways like the primes. There's a correction you have to do to Kramer's model in order to do some parts of some things. One of the things you have to correct for is that there's only one even prime, that's 2. And there's only one prime that's a multiple of 3. And there's only one prime that's a multiple of 5. And if you do that for the small numbers, you get a correction term. And this gives you correct guesses for many things, like how many 4-term arithmetic progressions are there up to n in the primes. And you get the right asymptotic by following Kramer's model and this correction factor. So this is how we try to understand the primes. And then proofs often try to use ideas around randomness to prove things about the primes. Okay, so the Green-Tao theorem says that the primes contain arbitrarily long arithmetic progressions, and these are some examples. The longest known example only has 26 terms. That's with a lot of computational power that it was found. You have to go pretty far out. Okay, so what are the ideas that go into the proof of the Green-Tao theorem? Well, it started with an idea of Erdős and Turon in the 1930s. Instead of looking at the primes are not dense, but they're fairly dense. Up to n, it's only density is 1 over natural log of n, so it's fairly dense. So instead of looking at the primes, Erdős and Turon said, let's look at any set that's dense. And they said, they conjectured that every set of natural numbers with positive density, so it contains at least 1 over 1,000 of the numbers up to n for each n, should contain arbitrarily long arithmetic progressions. And this conjecture of Erdős and Turon was open for a long time. The first case where it was proved was by Rosse in the 1950s. So if you take a subset of 1 to n, and it has no 3-term arithmetic progression, then the set is small. It doesn't have n elements. It has little o n elements. So the density, the size of the set divided by n tends to 0 as n goes to infinity. Now, Rosse gave a very nice proof using Fourier analysis. It was a very influential idea. So instead of looking at a subset of the interval 1 to n, he picked the cyclic group mod n. And you can see that they're essentially the same problem. And then he looks at the Fourier coefficients of the characteristic function of the set A. Now, why he does this is that there's a nice formula for the number of 3-term arithmetic progressions in terms of the Fourier coefficients. And if all the non-trivial Fourier coefficients are small, then this formula shows you that the number of 3-term arithmetic progressions is asymptotically the same as what you would get in a random set of the same density as A. And that would be a lot of 3-term progressions. So what this shows you is if there's no 3-term progression, then A should either be small or there should be a large Fourier coefficient. So if A is density alpha, we look at this large Fourier coefficient, and you can use that to find a long arithmetic progression where your set A is denser on that arithmetic progression than it was on the original cyclic group. And this set is almost linear in length. The problem is it's not an arithmetic progression in the integer sense, from 1 to n. It's in the cyclic sense. So you're going around on a circle, and you keep going around and around and around. And you'd like a real arithmetic progression where you get a density increment. So Rosse cuts up this arithmetic progression into smaller arithmetic progressions. And he gets an arithmetic progression of length roughly square root of n, where you get a density increment. So instead of your original set of density alpha within Zn, now your set A inside this arithmetic progression has density alpha plus roughly alpha squared. Some little density increment, but enough. And now it's a dense subset of a real arithmetic progression. And you just increment this because knowing the problem in an arithmetic progression is equivalent to understanding it in an interval. And so you just repeat the same thing. So each step you get a density increment. You start off with alpha. You go in from n to square root of n. You go in from alpha to alpha plus alpha squared. And you just keep repeating. And it tails off after some constant over alpha steps that you can't get density bigger than 1. OK. So this is the idea behind Roth's theorem, and the bound that it gives is n over log n. And it's not that great because each time you really shrink the interval a lot. You went from n to square root of n. Yes?
So you said that this is only because it works in integers over Zn. Is it only a singular?
It's the same proof. It's the same proof.
It is chopping up like this square root even when you're walking?
Yes, you have to do both, yeah. OK, so you lose log for that proof. And then there were improvements over various years by Heath Brown, Similarity, Bourgain, Sanders, and Bloom. There were 2 key ideas that came out from this. One idea of Bourgain was the big loss was that you went from n to square root of n when you got this density increment. You like to go from n to something that's nearly linear. So you like a big thing, but you can't get an arithmetic progression. So he introduces this thing called the Bohr set, which is a generalized arithmetic progression. And then you get a density increment on this Bohr set, which is very nice. It's almost linear, and you get some big density increment. The problem is then you have to do Fourier analysis on Bohr sets, and that's really ugly, but can be done. So that he goes from log n to log n to some power. So he gets rid of one of the logs, essentially. There's another nice idea is instead of looking at the single largest non-trivial Fourier coefficient, you look at all of them that are pretty large, and then you show that they have some additive structure, and that allows you to get a bigger density increment. And with all of those ideas, we're now at the bound of n over log n times log n to the 4th power. Now, if we didn't have this log n to the 4th power, if we had like a log n in the denominator or anything that was little o of n over log n, we would get that the primes contain lots of three-term arithmetic progressions simply because any set that's as dense as the prime should have lots of three-term arithmetic progressions. So the primes aren't special, they're just numerous enough. They're out there. There's a lot of them. It should definitely be the case. So any set that's as dense as the prime should contain long arithmetic progressions. They're not special. The only thing we needed to know is that there's a lot of primes. Now, another nice result, this is an amplification idea due to Varnavides, is not only will you get one arithmetic progression, but if you have a set of constant density alpha, then you get a constant fraction of all possible three-term arithmetic progressions in your set. So in 1 to n, you'll have on the order of n squared three-term arithmetic progressions. You have to pick the first term and the common difference, and you can do that and show that it's quadratic. Varnavides has this nice averaging argument that shows that if you have some constant density, then you'll have a constant fraction of all the three-term arithmetic progressions. So what about the other direction? Let's say we wanted to build a large set that has no three-term arithmetic progression. Well, a common technique in combinatorics would be to use the probabilistic method, take a random set. And the best you would get from this essentially is square root of n. If you try the most naive idea, you get about cube root of n. And if you do other methods, you get to square root of n. There's another nice idea due to Richard Stanley, so these are called Stanley sequences, is just greedily construct a set that does not have a three-term progression. And it's convenient to start off at 0 instead of 1. So let's start at 0. And well, our set doesn't have a three-term progression yet. And we can add 1, and we still don't have a three-term progression. So then we get to 2. Now 0, 1, and 2 form a three-term arithmetic progression. So we're not allowed to include 2. So we skip it, and we go to the next number. 3, we can include that. There's still no three-term progression. 4, we can include. There's still no three-term. We get to 5, we have 3, 4, 5. When we get to 6, we can't do that because we have 0, 3, and then 6. So if we added 6, we'd create a three-term. And you can continue in this way, and you'd get the sequence that has no three-term arithmetic progression just by greedily adding elements one at a time, as long as you can. Now, it's not immediately obvious what this pattern is. Maybe it is to some of you, because I wrote it in base 10. So if you write it in base 3, it's a really simple pattern. Here's what the base 3 representation. So in base 3, the sequence is precisely the numbers that do not have 2 in their base 3 representation. So up to the first 3 to the r numbers, you get 2 to the r numbers by picking 0 or 1 in each coordinate. And of the n being 3 to the r numbers, you get n to the log base 2 divided by log 3 numbers, which is n to the 0.63, which is better than a half, but still not close to 1. So it is known how to get to 1. There's this very nice idea of Barron that uses high-dimensional geometry. And it's a simple construction, and it gets a three-term AP-free set, so no three-term arithmetic progressions, of the first n positive integers of size almost linear, n divided by e to the root log n. So it's n to the 1 minus little o1 size. And this is roughly the best that's known, and many people believe this is the right answer for this, essentially. So I'll explain what the construction is. It'll be pictures. And so we like a large subset of 1 to n without a three-term arithmetic progression. So we're going to use high-dimensional geometry. So instead of picking an interval, we'll first do a simpler problem, try to take a large subset of a grid without a three-term arithmetic progression. So no 3 points where the second point is the average of the first and last point. So we have a grid, and we'd like a large subset of this d-dimensional grid. I don't know how to draw more than 3 dimensions. So this is 3-dimension grid, n by n by n, but you should think about d dimensions because really we'll like to take high dimensions. So we like a large subset of this grid which has no three-term arithmetic progression. And how do we do that? Well, one set that has no three-term arithmetic progression, one type of set is a sphere. A sphere is convex, and so we're taking just the exterior, not the interior. So we're taking the surface. Why does a sphere not have a three-term arithmetic progression? Does anybody see this? Yeah, so the 3 points will be on a line. And if you intersect the sphere with a line, you'll get at most 2 points. The reason is the first and third term of the arithmetic progression that you're looking for, they're on the sphere. The midpoint's in the interior of the sphere because the sphere is convex. So the sphere doesn't have any 3-term arithmetic progression, so any subset of the sphere will also not have a 3-term arithmetic progression. So we'll find a sphere that intersects the cube in as many points as possible, the grid points. These are grid points here. And we'll try to find a sphere that intersects it, and you can find a sphere that intersects in a lot of points. Okay, but now we have a subset in d-dimensional space without a 3-term arithmetic progression. How do we get a, that's not what we were looking for originally. We want a subset of 1 to n without a 3-term arithmetic progression. So the next idea is to project it down to the line. So you project any point of the grid to the interval by taking the point x1 to xd and basically writing it in base 2n and adding 1. And that gives you a projection. And then it's a simple check to show the fact that the original set doesn't have a 3-term arithmetic progression. With this choice of projection, this is a linear map, you still will not have a 3-term arithmetic progression, and you'll have a lot of points. And then you have to pick the parameters little n and d appropriately. So your big N, that interval is 2n to the d. This was done in the 40s, and people have tried hard to improve on this construction. There was a small improvement by Elkin a few years back. Instead of looking at the sphere, he fattened up the sphere. He made it a little bit thickness, and that allows for some 3-term arithmetic progressions, 3 points that are really close to each other. You'll get a very small number of 3-term arithmetic progressions. You can delete 1 point from each of them. And if you do that carefully, you get a very small improvement. But it does improve a little bit on Barron. But roughly the idea behind Barron seems to be the best possible. There's questions that are very close to finding a 3-term AP-free set. So not having a 3-term AP 3-term arithmetic progression is equivalent to forbidding a solution to the equation x plus y equals 2z in distinct x, y, and z. And if instead of this equation you look at longer equations with 4 variables instead of 3, and you pick it correctly, then you'll get upper bounds that get close to looking like the Barron lower bounds. And so there are various reasons why, using Fourier analysis, there's various reasons why this seems to be close to the right answer. Okay. Good. Now that's just for 3-term progressions. And already that was in Ross field medal citation. That was probably his second most famous theorem. Then in the 70s, Similarity proved the Ariston Conjecture. So every set of natural numbers with positive upper density contains arbitrarily long arithmetic progressions. Similarity's proof introduced a really powerful decomposition result for graphs called Similarity's Regularity Lemma. This has been really influential in combinatorics and in theoretical computer science. And it's also useful in number theory. For example, in the proof of this result of Similarity. Now, this itself is getting in the direction of proving that the primes contain long arithmetic progressions, but the primes we said aren't dense, they're close to dense. So how do Green and Tao then prove their theorem? Well, they do the following. They strengthen Similarity's theorem. They prove something called the relative Similarity's theorem. And so the setup for this is we have this set of prime numbers. They make a little bit larger set Q, which we call the almost primes. And roughly, you should think about this as numbers that have few prime factors, and they're all large. So these are the almost primes. This is a rough cheat, but it's almost the correct idea. You can tweak it a bit and make it correct. And the set of prime numbers will be relatively dense in this set of almost primes. And then you can show that the almost primes behave in many ways like a random set. Just like this Kramer's model idea from earlier about the primes, you can show that the almost primes have very strong quasi-randomness properties, pseudo-randomness properties, and then you prove a relative similarity theorem, which uses Similarity's theorem as a black box in order to prove it. And it says that if a set S of natural numbers satisfies certain pseudo-randomness conditions, then every dense subset of S contains arbitrarily long arithmetic progressions. So that's the first step, is to prove a relative similarity theorem. And the second step is to construct a superset of the primes that satisfies these conditions. And the question then that's important is, what are these pseudo-randomness conditions that you need to have? And Green and Tao proved that if they satisfy two conditions, one's called the linear forms condition. And that's basically saying if you have certain systems of linear equations, the counts are roughly what you expect if the set was random. And then there's a much more complicated and harder to work with condition called the correlation condition, which doesn't have such a nice way to describe it. And people had asked to get rid of or weaken these conditions. So it's known that you need some conditions, but what are the right conditions in order to prove a relative Similarity theorem? And this was asked by many people. And with David Conlin and Yufei Zhao, we answered this problem. We got rid of the correlation condition and showed that a weak linear forms condition is enough. And this proof is based on the graph theoretic ideas that started with Similarity in his proof of Similarity's theorem. There's been a number of recent works which extend the Green-Tao theorem. So for example, Terry Tao and Tamar Ziegler proved that not only do the primes contain arithmetic progressions, but they also contain polynomial progressions, and even in short intervals. And it was essential for their work to use this form of it because the correlation condition caused serious problems in their work. It's a difficulty. Okay, so that was talking about numbers. I next want to move to graphs. So graph theory has developed quite rapidly with the development of computer science. A graph has a vertex set V and a set E of edges, which are pairs of vertices. So this is a drawing of a graph with 6 vertices, labeled 1 to 6. And between certain pairs of them, there are edges, and those are denoted by line segments. So this one only has 6 vertices, so it was pretty easy to draw. But some of the graphs we want to look at have billions of vertices. And we want to run algorithms on these graphs, and we want to understand them better. So as some examples, the internet, which has computers connected by links, or the World Wide Web with web pages and hyperlinks connecting certain pairs of them. There's social networks like Facebook. Many people are on Facebook. In fact, there's over 2 billion users on Facebook, and certain pairs of them are friends, so they're linked by friendships. There's chemical networks that we want to study with atoms and chemical bonds. Biological networks like the brain with neurons and synapses, and engineer networks like chips with transistors and wires. Each of these examples can have over 1 billion vertices. And you'd like to understand these graphs better. These examples are documented in the book, the nice book by Lovaas, Large Networks and Graph Limits. Okay, so that's graphs, and we like to understand their structure, which will tell us a lot about what properties the graphs have. And there's this amazing regularity lemma that Similarity introduced in his proof of Similarity's theorem. So this is, it roughly says that every graph can be partitioned into a small number of parts that are roughly equal size. That's not really a big deal, but the main thing is that the graph is random-like between almost all pairs of parts. So if you look at a typical pair of parts, the edges between them behave random-like. And in what sense do they behave random-like? So we'll get into that shortly. This is a rough structural result for all graphs. So every graph has a Similarity partition, and it's one of the most powerful tools we have in graph theory. So you need to bear with me to go through a few definitions in order to understand what's actually going on here. So this is a rough idea of the result. The actual idea looks at density of edges between subsets. So let X and Y be vertex subsets of a graph. You have a graph G, it has a vertex set, and we're going to pick these vertex subsets, X and Y. And you count the number of edges between X and Y. If they're disjoint, you're really counting the number of edges that go from X to Y. They could overlap X and Y, and then you would count the edges inside twice. So you're counting the number of pairs in X times Y that are edges. That's EXY. And the edge density between X and Y is the fraction of pairs between X and Y that are edges. So it's a number of edges, EXY, divided by the product of their sizes. And then this is the key definition, irregularity. The irregularity between two subsets of vertices, X and Y, is the maximum over all subsets A of x, so you pick out any subset A of x and B of y, of the absolute value of the number of edges between A and B minus the number of edges you'd expect there to be between A and B, given the edge density between x and y. These are subsets, so you expect the density to be typically around the density between x and y times the number of pairs between A and B. So if you took a random subset A of x and B of y, this is how many edges you'd expect there to be between A and B. And you look at the maximum of this, the actual number minus the expected number. And you take the absolute value and you look at this over all, so you're looking at the maximum over all A, a subset of x, and B, a subset of y. And if the graph was truly random, this irregularity would be small between x and y. And so it's a measure of the randomness between x and y. And you call a pair xy epsilon regular if the irregularity between x and y is at most epsilon times the size of x times the size of y. And so it could be all the way up to some constant times x times y. And it's going to be small. If it's small, it means, so if it's epsilon regular, it's saying that the edges between x and y behave random-like. Okay, so we have this notion of irregularity between a pair of subsets of a graph. What about the irregularity of a vertex partition? So we have a vertex partition of a graph. We just sum up the irregularities between all of the pairs of parts of the partition. And then the irregularity, so if the irregularity is small, at most epsilon times the number of vertices squared, then you call the partition epsilon regular. And that's basically telling you that most parts are, so it's really telling you on average the parts are epsilon regular. And what Similarity regularity lemma tells you is that for each epsilon greater than 0, there's some epsilon, m of epsilon. It only depends on epsilon. So that every graph G has an epsilon regular vertex partition with at most m of epsilon parts. So it's a bounded number of parts, and it only depends on epsilon. And so this is an incredibly useful tool. So you'd like to have m of epsilon to be small. You don't want to cut it up into too many pieces. And the proof of the regularity lemma gives an enormous upper bound on m of epsilon. So you have to introduce a tower function, T of n. If you haven't seen the tower function before, this is 2 to the 2 to the 2 to the 2 to the, okay, n times. It's a really fast-growing function. And in this area, this type of function comes up often, and then even faster-growing functions come up often. I won't introduce the faster-growing functions here, but yes, so this is the tower function. And the upper bound that you get from Similarity's proof is a tower of 2's for m of epsilon, which is at most a constant times epsilon to the minus 2. That's what the proof gives. And for a long time, people thought that maybe one could improve this bound and get better bounds for the various applications. In particular, there's a very nice proof of Rosse theorem that follows from an application of Similarity regularity lemma. So if you had a really good proof for this that had good bounds, then you would get good bounds for lots of its applications. Unfortunately, Gowers gave this nice probabilistic construction in the mid-90s, which shows that actually you need a tower-type bound. So there are some graphs that need a tower in some power of 1 over epsilon number of parts in any epsilon regular partition. And he had asked to determine the order of the tower height here. And this was solved last year, well, it was published last year, by my student Laszlo Miklos-Lovas and myself, where we determined that, in fact, the upper bound that comes from Similarity's natural proof is correct up to an absolute constant factor. So it really is tight. It's, and we understand this. Unfortunately, it goes in the way, the negative way for applications. Okay. So more generally, there's a powerful tool here that comes in combination with the regularity lemma called the counting lemma. So why is the regularity lemma so useful? Well, you use it together with a counting lemma. If you have three subsets of a graph, x, y, and z, and each pair of them are epsilon regular, and you wanted to count the number of triangles with one vertex in each of the parts, you would expect if the edges came randomly with a given density between each pair of parts, that the number of triangles would be the product of the three edge densities times the product of the sizes of the three sets. And what the regularity lemma says is if each pair is epsilon regular with epsilon small, then indeed it's close to that. It's within 3 epsilon times x times y times z times the count you get here. So in general, you would use these things in combination, and a nice example application, which has itself many applications, including Rosse theorem, is the triangle removal lemma of Rosse and Similarity. So it says for any epsilon greater than 0, there's a delta greater than 0 if you have a graph with few total triangles. So a graph on n vertices that has up to n choose 3 triangles, which is cubic in n. If the graph has few total triangles, at most delta n cubed, it explains why it has few triangles. It can be made triangle-free by removing epsilon n squared edges. That's the only way you have few triangles, is that your graph actually was a hidden triangle-free graph, and you sprinkled some extra edges, some small number of extra edges on top of it. And for the various applications, you'd like to have a good dependence of epsilon on delta. The proof of this, the standard proof, uses the regularity lemma. You apply Similarity's regularity lemma. And then you delete edges between pairs of parts that are irregular. So there's a few pairs that can be irregular. We allow for that. And so you won't delete too many edges between those parts. And you also delete edges between pairs of parts that are sparse. And again, you won't delete many edges. So in total, you'll have deleted at most epsilon n squared edges. And if there's any triangle that remains after you've deleted this small number of edges, then the edges go between parts which are both regular and dense. And then from the counting lemma, we know that in fact we'll have a cubic number of triangles, which implies that the original graph had a cubic number of triangles, bigger than the delta n cubed. So, so you either have no triangle in what remains and you've deleted few edges to get there, or you had lots of triangles to start with. Okay. So what is this dependence? Well, the proof that comes from using the regularity lemma gives an upper bound on 1 over delta, which is a tower of 2's of height, a power of 1 over epsilon. And we'd like to improve this bound, and still the best known bound is still a tower type. Instead of height, a power of 1 over epsilon, it's a logarithmic in 1 over epsilon. And this is a result that I proved toward the end of my PhD. And the lower bound is very far off. It's just slightly super polynomial. It's quasi-polynomial. And it's based on this Barron's construction we saw earlier. So the proof, there's a nice proof of Rosse theorem using the triangle removal lemma. And reverse engineering that proof gives you a lower bound on the bound in the removal lemma, which is slightly super polynomial. And there's this enormous gap between a tower function and something that's not even exponential. It's an interesting problem to close the gap here. I'm not sure. Yeah, I've worked on both directions, and I don't know. It's stuck at the moment. But okay. So what about triangles in large graphs? When I was an undergraduate at MIT down the street, I was walking down the hall one day, and I noticed on one of the classroom doors, there was a sign that said, "Class today is closed due to terrorism." And I was surprised by this. And there was no imminent harm. There was a visiting professor who was teaching a class, and he was working on counterterrorism. He was interested in finding terrorist cells. And so he was working on this, and in particular, he was looking for cliques in large networks. And this is exactly what this type of question is. So there's many other reasons why one might want to study questions about structures in large networks, but for him, that was one motivation. Okay, so let's look at triangles and large graphs. For example, are there 3 mutual friends on Facebook? So you'd like to find 3 people on Facebook that are, each pair of them are friends. Well, that's a pretty easy thing to do. You can, if you have a Facebook account, you might have 100 friends, and probably a pair of them are friends, and you and that pair of friends are friends. Now, if I ask you the same question, but it's not the Facebook graph, I just give you a graph and the same number of vertices, 2 billion vertices, and I ask you, find a triangle in this graph, then this is a harder problem. The natural attempt is to check all n choose 3 triples of vertices. And that's more than 10 to the 27 triples of vertices. And a back of the envelope calculation says that that's going to take a long time, roughly 100 billion years, with a standard computer, something like this. Okay, so that's not a very good thing. So let's look at attempt 2. Attempt 2 is to use some additional idea. Let's look at the adjacency matrix of the graph. So this is the same graph from earlier. It has 6 vertices. You make the adjacency matrix of a graph with n vertices. It's an n by n symmetric matrix. There's a 1 in the ijth entry if vertex I and vertex j are adjacent. And there's a 0 otherwise. So it's a 0, 1 matrix. It's symmetric. And you can check that the trace of the cube of the adjacency matrix is 6 times the number of triangles. More generally, if you take the adjacency matrix to the kth power and you look at the ij entry, it's the number of ways of walking from vertex I to vertex j by a walk of length k. And if you look at a diagonal entry, the ith entry of a cubed, that's counting the number of walks of length 3 starting at I and ending at I. Well, that's twice the number of triangles that vertex I is in. So if you add all of the entries along the diagonal, that's the trace, and that's going to end up being 6 times the total number of triangles. So if we want to find a triangle in a graph, we actually can count the number of triangles by computing 6 times the trace of the adjacency matrix cube. Now, the standard thing to do here, when you multiply 2 matrices and take the product of each row and column vector, that will take cubic time. But there was these improvements by Strassen, and then Coppersmith and Vinograd later, and then there was more recent work by Stothers, Virginia Williams, and Lafall. And right now we know how to do it in time roughly the number of vertices to omega. Now, they gave it a name because it comes up so often in computer science algorithms. So the best known exponent we know, omega, is about 2.3728. But it's probably 2, and we just haven't gotten there yet. So probably there's a nearly quadratic time algorithm. Basically, it takes you as long, a little bit longer than reading the 2 matrices to multiply them. So that's what we think, but we're still far away. And from that, and doing this only takes about 50,000 years from a back of the envelope calculation. Okay, that's still pretty bad. So we really don't want to look at the whole graph and do something there. And this leads to the idea of property testing. So you like these really fast algorithms. You have to give up something, though. If you're trying to say a graph is triangle-free, you really should be able to have to check everything there. And instead of being able to say whether a graph is triangle-free, you'd like to be able to quickly distinguish between a graph that's triangle-free and a graph that's far from triangle-free, that you'd have to delete at least epsilon n squared edges in order to make it triangle-free. So you give up something. This is known as property testing. You want to quickly distinguish between objects that have a property from objects that are far from having that property. This idea was introduced by Rubenfeld and Sudan in 1996 and investigated more further for combinatorial objects by Goldwasser and Rahn. So a testable graph property, you call a graph property P testable. So for example, P could be triangle freeness. If for each epsilon greater than 0, there's a randomized algorithm which in constant time, depending on epsilon and the property P, distinguishes with probability at least 2/3 between graphs having the property P and graphs which are epsilon far from having P. And these are essentially, the testable ones are essentially properties where you get a removal lemma, just like we saw the triangle removal lemma earlier. And so they're pretty vast generalizations now of the triangle removal lemma. Basically, any natural graph property is testable, and I won't define that explicitly, but it is the case, and it uses all these ideas around regularity. But I'll show you that triangle freeness is testable. So the idea is you pick 1 over delta random triples of vertices from your graph, and delta here is the delta from the triangle removal lemma. It's the same delta, so it's going to be pretty small if epsilon's small. And you accept if no triple that you picked out forms a triangle. So you pick out these triples of vertices, and you look, are they a triangle? Do they form triangle or not? And if none of them make a triangle, you accept. You say, okay, this is going to be a triangle-free graph. Well, it may or may not be, but and you reject otherwise. If you see a triangle, then you say, oh, that's definitely not triangle-free. And if the graph is triangle-free, you won't get any triangles when you sample. So the algorithm accepts. But if that graph is epsilon far from being triangle-free, then from the triangle removal lemma, you know that there's at least delta n cubed triangles. And there's only n choose 3 triples, so the probability that you picked a triangle is at least 6 delta. And so that the probability that you missed a triangle is at most 1 minus 6 delta. And you picked 1 over delta random triples independently. And so the probability that you always miss a triangle, even though you're epsilon far from being triangle-free, is at most 1 minus 6 delta to the 1 over delta. And you can do some simple computation and see that's less than 1%, that you made an error. And so in this way, you can test triangle freeness. So you can distinguish between triangle-free graphs and graphs that are far from triangle-free by doing this quite quickly in the sense that you don't have to depend on the number of vertices of the graph. There is this problem here that you picked 1 over delta random triples and then had to test all of those. And so you'd like delta to be, 1 over delta to be pretty small. And that means you'd like delta not to be too small itself. And so it really comes down to what are the bounds in the triangle removal lemma. It's essentially the same problem as understanding this question. Okay. So the tower bound that we get is a major drawback of the regularity lemma. And it's a major open problem to find alternative proofs of applications which avoid using the regularity lemma and give improved bounds. And we're going to talk about that in the arithmetic setting shortly. So first, I want to introduce this game called Set, and then we'll explain the connections to what we've already seen. So there's this game called Set. It's a card game. So in the game of Set, on each card, there are some shapes. There's either 1, 2, or 3. It's the same shape. There's a certain shading. It's either solid, striped, or open. The color, it's either red, green, or purple. And the shape is either oval, squiggle, or diamond. And there's 81 cards in total. And you can correspond each card to a point in F3 to the 4. Because you have 4 dimensions here and 3 options in each. Okay, so you can view the cards as points in the vector space F3 to the 4, just like you looked at vector spaces over the reals. You can look at a vector space over a finite field, in this case 3 elements. F3, this is just clock arithmetic, but with only 3 hours instead of 12. So 3 cards form a set if all are the same, if all the same or all different in each attribute. So you look at the number, and on each card there's only 1 shape, then they're all the same. And if it's 1, 2, and 3, then they're all different. And you look at each attribute, and in each attribute, the 3 cards, you like them to be all the same or all different. And that would form a set. And you're trying to build sets in this game. So here's the full deck of cards. That's 81 cards. This is from the nice Quanta article about this. And these are some examples where you have a set or no set. In the first column, this is not a set, because in color, there's 2 that are green and 1 that's purple. So they're not all the same or all different. If you look at the third one, in each property, they're all different. And in the last one, in some properties, they're all different, and some of them, they're all the same. And so you can see that forms a set. Okay, so here's an example of 12 cards. This is how the game's played. You put out 12 cards. And the first person to find a set gets to keep the cards. So there's 12 cards. I bought these cards yesterday at the Harvard Coop. So here are 12 cards. Does anybody see a set yet? Yes? Yes, so I conveniently placed 3 cards in the top row, making in the first 3, the green diamonds up there. The first 3 cards in the top row. Right. Good job. And you checked all 220 possibilities. And that was very quick. OK. Now, if you looked at this set, this 12 cards, you tried to find a set, you would discover that there is none. And if I had put these cards down randomly, there's only a 3% chance of that happening. But does the game end there? The answer is no, you put 3 more cards down. OK, so now you have 15 cards. There's probably a set here. Well, if it was random, there would likely be a set. It's a 1 in 30,000 chance that there's no set. But in fact, there is no set because I picked this carefully. OK, so now here's 18 cards. And you can check again, there's no set. And if these were randomly picked 18 cards, there's a 1 in 70 million chance of this happening. So I very carefully picked these out. And then here's 20 cards without a set. And if you tried to pick that out, well, so that's 1 in 7 trillion chance of that happening. Can you get any more than 20 cards without having a set? And as you can tell from the title of the slide, the answer is no. So this is the maximum number. It's proved using a big computer search. OK, so this is a card game question. And there were 4 attributes here. And you can actually ask these sort of questions with more attributes. So instead of 4 dimensions, what about n dimensions? And this is called the cap set problem. How many of the 3 to the n cards can we have with no set? So instead of 4 attributes, we make n. We have 3 to the n cards. How many of them can we have with no set? Now, it seems like a toy question, but it turns out that it's closely related to several famous questions, important questions in combinatorics and number theory and computer science. For example, if we view the cards as points in F3 to the n, a set is exactly a 3-term arithmetic progression. So we want a large subset of F3 to the n without a 3-term arithmetic progression. And the ideas that have been used to understand Rosse theorem become much easier in this setting. And so this became a toy problem for understanding Rosse theorem. So that's one reason why people studied it. But another reason is if you could build a set with almost 3 to the n cards without a set, then you could improve the speed of matrix multiplication to almost quadratic. And so people really wanted to understand this problem well. And there were other classical questions in combinatorics, the Aridus Similarity sunflower problem, which were essentially equivalent to understanding the bounds here. So over time, there were various improvements. They were all roughly 3 to the n. And then there was a big breakthrough by Krutlev and Pak, where they, instead of F3 to the n, they looked at Z4 to the n, the cyclic group mod 4 to the nth power, and they proved an exponential improvement for that. And within a couple days, Ellenberg and Geisweit had improved the upper bound along the same lines to 2.756 to the n. So instead of getting a roughly 3 to the n bound, they got an exponential improvement. And instead of using these analytic ideas from Fourier analysis, which all the previous results essentially were based on, they used the polynomial method, which has become a really powerful tool in combinatorics over the years and in some related areas. So this was a huge breakthrough in about May of 2016. And we're still proving new things and understanding this better. So instead of looking at the set problem, there's actually strengthenings that people have looked at over time. Suppose you have 3 people, Alice, Bob, and Kathy, and they each have set cards. So with n attributes. And a set is rainbow if each person has one of the cards. So you have these 3 players. They each have some cards. They could have even the same cards. They each have some subset of the total number of a full deck. And if what Blasiak et al. And Noga alone observed is that if each card is in exactly one rainbow set, then you get the same bound on the size of the number of cards that each player can have. It's the same proof. It just goes through. It generalizes. Why is this a generalization? Well, if each of the Alice, Bob, and Kathy have exactly the same set of cards, and there's no, in that set, there's no set, then you get exactly this setup where each card is in exactly one rainbow set. Precisely that card's repeated 3 times is a rainbow set in that instance. There was a generalization of this proved much earlier by Ben Green with by developing an arithmetic regularity lemma. So he proved an arithmetic triangle removal lemma. In this case, it says that for each epsilon, there's a delta greater than 0, such that if there are at most delta n squared rainbow sets, so there's few rainbow sets going across the 3 players, then you can remove a small number of cards from each player and get rid of all the rainbow sets. And the way that he proved this was developing this arithmetic regularity lemma, which is an analog of Similarity regularity lemma. Again, it requires tower-type bounds. So you get these really awful bounds. And he asked if a better bound can be proved. In particular, can you get a polynomial dependence there? And using some combinatorial and probabilistic ideas, we were able to amplify the work about when each card is in exactly one rainbow set. This was Laszlo, Miklos, Lovas, and myself. And we proved that, indeed, there's a polynomial bound, that delta is roughly epsilon to the 13.901. So there's an explicit constant. You can write it down, but it takes a long time to actually write down. It would take up a board to write. And you can write down what that constant is using some logarithms and square roots and polynomials and things. And it turns out to be roughly 13.901. And you can take delta to be epsilon to this constant. And this is the best possible constant that you can get. So there's a construction that matches this. And it comes from an optimization problem that's much more natural than what you see from the formula. OK. So this turns out to be closely related to arithmetic property testing, and there's been some recent work on generalizing this. I want to mention one last thing, and well, 2 last things, hopefully briefly. So soon after the CAPSET result was proved, my son, David, he was 6 at the time. He really likes playing with the card game set, and he had these set cards, and he came to me really excited. He found 9 cards where he could find a lot of sets between them. He found 12 sets amongst these 9 cards. He was really excited. And what I realized was that he found a 2-dimensional affine subspace. So that's equivalent. And so if you have 9 cards and you get a 2-dimensional affine subspace. And I had this great, there was this great undergraduate student who I asked to try to go through the probabilistic method and solve all the problems and do all these other things. He took my graduate class and did really well. And he wanted to do a research project. And so I thought, why don't we try to look at some questions around the CAPSET problem? One way to think about the CAPSET problem is in F3 to the n, you're asking for a subset of F3 to the n that does not contain a line. It's equivalent to not having a 3-term arithmetic progression. It's equivalent to saying it in terms of these cards. It's equivalent to the 3 numbers not adding up to 0. There's a lot of different ways to interpret it. So this is you can ask the same question without a 2-dimensional affine subspace. And right, and so it turns out, so you can ask how many elements can you find in F3 to the n which does not contain a d-dimensional affine subspace. And you can try going through this polynomial method that people have been using, and unfortunately it fails. The complexity of this, with the right notion of complexity, is too large. But there's a simple averaging argument that works that allows you to prove an improvement on the exponent. And this 13.902 is the constant that comes from the triangle removal lemma. And this lower bound comes from just considering a random set. And so you get this exponential type improvement. And one of the things I was interested in was what the right exponent is. Is it 3 or is it 13.902? And the way that you prove the upper bound is if your set has density alpha, you can look at the density of lines you get. That's a density of sets. And from the triangle removal lemma, you'll actually get alpha to the roughly 14 density of sets. And this 13.902. And so there's going to be some direction where you get a lot of lines, density at least alpha to the 13.902 of those lines in that same direction. And if you squish along that direction, you can keep a point from each of those lines where you have the entire line. You'll have a subset of n-1 dimensional space with density alpha to the 13.902. And then again, you apply the CAPSET result, or the arithmetic triangle removal lemma, you'll get a lot of lines in that set. And then together, those lines with where the original direction you came from would create a two-dimensional affine subspace, and you can iterate this idea. So you'd like a direction where you get a lot of where you get a lot of lines. That's equivalent to finding a certain common difference that appears very often in three-term progressions in your set. So that led us to study a different problem. This is the final slide. That originally, there was a conjecture of Bergelsen, Host, and Craw, and it was solved by Ben Green. If you're given an epsilon greater than 0, there's some n that only depends on epsilon, such that if n is big enough, and you have a subset of 1 to n, of density alpha, for whatever alpha is, then there is a non-zero d such that there are a lot of three-term arithmetic progressions with common difference d, at least alpha cubed minus epsilon times n. Now, why is the alpha cubed there? Well, that's the random bound. If you looked at a random subset of 1 to n, the probability that a three-term arithmetic progression is in your set is alpha times alpha times alpha, alpha cubed. So the density of three-term progressions should be alpha cubed in a random set, but there are constructions of sets with a lot fewer three-term progressions. And what this result is telling you is at least for 1D, you can attain the random bound. That the total number of three-term arithmetic progressions is at least the random bound, maybe minus this, there's a little epsilon there in the density. And so if you had good quantitative estimates for this problem, you'd have solved the previous question of finding the asymptotics. Instead of this 13.902, you'd get the 3 there, matching the random bound. So we wanted to get better upper bounds on this n of epsilon that comes from this problem. And the proof of this used the regularity lemma, so you get this big tower type bound. And so how large is this n of epsilon? In joint work with Hui Pham and Yufei Zhao, who's here, he's on the faculty at MIT, we showed that, in fact, the correct answer is a tower function of height on the order of logarithmic in 1 over epsilon. So you need n to be absolutely enormous, a tower of 2s of height logarithmic in 1 over epsilon for this theorem to hold. There's a construction that matches an improved upper bound that we got, and it's same holds in some more general settings as well. The thing that got me really excited about this is in this whole field for a long time, we've been trying to get rid of using the regularity lemma. So Similarity been the one pushing this the most, that you should not use the regularity lemma. You should find a better way to prove your results, and that would prove it, and you'd understand the problem much better, and you get better bounds. And this example shows, at least for this application, we found some more now as well, that you actually need these tower type bounds. And so we're learning a little bit more about what's going on here with these sorts of applications. And I'm over, so thank you.
So you had a bunch of conjectures at the beginning.
Yes.
Number theory conjectures.
About the primes, yes.
And is there a sense that regularity could help them in any of the other conjectures?
Well, I'm not sure about regularity in the strong, maybe, but I mean, the key idea that's been involved with all of these is this idea of randomness, that the primes or supersets of the primes behave random. And the idea is a number theory using Fourier analysis and other techniques like that. Behind all of it is the idea of either things behave randomly and you can count things, or you can't. But there's some fundamental issues that these are rather degenerate problems. And so the less degenerate ones, these techniques work very nicely. And for these very degenerate ones, it seems we don't know what to do, but possibly, yeah.
Running a lot of time, and I guess some people have to go to their meal plans. Let's break the speakers and take more questions. Maybe
Offline, yeah. Thank you.